Hey guys, welcome to the tutorial on dynamic programming. In this tutorial, what I will be explaining is the concepts of dynamic programming, the important questions which are asked in companies placement in IITs and different NITs. So without any ado, let's start with our first code. So in this, what we're gonna do is we have given an array of elements. So the elements contain duplicate elements also. Given the elements, what the task is, we have to find the maximum sum with no adjacent element. Now what we gonna do is, let's say, suppose these are the set of elements we have. So what we need to find is, we need to find the sum of elements with no adjacent element. So it can be either this, this. Okay, so this will produce one sum with no adjacent element, or either it could be 10 plus 7 plus 14. This also constitute to one sum. There are many other possibilities also. Let's say we can take 7, 12 and 14 also. This also constitute to one sum. We can select 10, 7 and 14 also. So there are many possibilities in which we can take those elements whose sum which we take has no adjacent element with it. Okay, so what we're gonna do is, first I will be showing you the recursive method of solving this, and after that we will switch to dynamic programming. So let's say we have these elements, okay, and currently our pointer is this location. So first I will be discussing about recursive method of solving this. Okay, so let's say our pointer is at this location. Now we have at this point two possibilities. Now what these two possibilities are, either we can take this element and sum up with the rest of this part. We can't take this 9 because 9 is adjacent to 14. So if we take an element 14, so we are left with the elements 7, 10, 12 and 7. Otherwise, the other possibility is if we do not take this 14. So when we don't take this 14, we are left with 5 elements, that is 7, 10, 12, 7 and 9. Okay, so likewise in this left part, if we take 9 to be our part of the possible sum, and if we take 9, then we are left with these three section or these three portion, 7, 10 and 12. Likewise, if we do not take this 9, then we are left with 7, 10, 12 and 7. So as you can see, this is the section of part which is computed twice. Likewise, there are many parts which need to be computed twice. So whenever we are encountering this situation in which there is a possibility of a function calling itself multiple times with the same number of arguments or same values, then that method lead to a very costly operation. So let's say in this method, every time roughly we are dividing the portion into two parts. Okay, so two parts here, also two parts, in this also we are dividing it into two parts, and so on. So roughly we are dividing each portion two parts. So its complexity will be O of 2 raised to n. Okay, so what we gonna do is, so this is an exponential complexity. So as we know, this is the very costly operation. So we need to do one thing. We need to boil down to either quadratic or linear or constant. Constant is best one. Okay, so let's check this recursive method and try to code it out, and I will show you how to do this, and after that what we're gonna do is we will jump to the dynamic programming. Okay, so let's move to the coding section of this. See what we have an array of 6 elements, and let's say if we take its size, so this is the method or way in which we calculate the size of an array. So what we have this. So we are creating a function which we call it as method1, and we are passing an array and the size of the array. So first I will show you the recursive method of doing this. And here s is the size of the array. Now whenever we are writing any recursive function, make sure or keep in mind that we have to write the base case first, because without base case what will happen is our code will go into infinite loop or it will crash. Okay, so what we're gonna do is we're gonna write the base case. So whenever we reaches out of the index, let's say if we reach out of the index, or let's say if we take this as index -1, or if we take this as currently our index. Okay, if our index goes beyond 0, then what we're gonna return is we're gonna return simply 0. If our index is simply 0, then what gonna return is we're gonna return array of 0. And recursively what we're gonna return is we're gonna return the max of method 1 passing the array with the current index -2 or index -1, or if we include that array element present at that index, then we can't take the adjacent element, so we have to take the index -2. Okay, so this is the way we call the recursive function. So what this gonna do is, let's say we have these elements 7, 10, 12, 7, 9 and 14. So here in this case what we gonna do is we are not including this element and we are simply taking this element. So we are passing the function with the array and the index 1 less than this. If we take this element which is present at this index, then we can't take this index. So here our index is this, so we have to jump 2 back because we can take only this element, we can't take this adjacent element. So we are at with index -2, so here we are passing index -2. Okay, now what we have this. Okay, so and whatever is returning from that method we are printing here. Let's say what we gonna produce. Okay, so here index. Okay, cool. See, so it will produce a sum of 33 with maximum element and no adjacent elements. Okay, maximum sum with no adjacent elements. So let's look at this, how this sum is produced. So if we take this 7, 10, 12, 7, 9 and 14, so it may be generated because of this 14 plus this 12 plus this 7. So with sum of these three, it will produce a sum of 33. So this is the first method by which I showed you that how a recursive function help us to calculate the maximum sum with no adjacent element. Now I will be discussing about the next method of doing this. Now in this case let's analyze the time and the space complexity. Okay, so if we use the recursive function, we know that each and every step we are dividing the array into two parts, so which roughly costs at around 2 at each point. So our complexity boils down to 2 raised to n, which is exponential, which is very costly. And our space complexity is the size of the stack, which will go up to of log n with base 2. So this is the time and space complexity when we use the recursive function. Now next I will show you the DP version or dynamic version of doing the same thing. Okay, so let's say we have let's say if we take this example same again, and now instead of doing the iterative version or recursive version, what we gonna do is we gonna do the DP version of this. Let me take down the values again: 7, 10, 12, 7, 9, 14. Okay, now as we have already seen that the values are computed more than once, so we need a DP. So what's the use of the DP? Whenever we compute some value, whenever we compute some value, and if it is if we need that value again, then we use, whenever there is possibility of using the same code or same function again, we use the dynamic version of the code. So in this, what we gonna do is we create an array of size 1 greater than the number of elements present in our array. So here we have index, let's say 0, 1, 2, 3, 4 and 5. So we created an array of size 6. 0, 1, 2, 3, 4, 5, 6. Okay, so initially at 0th location we fill the value of 0, because with 0 element we have maximum sum of elements as 0. In the first element, that means it represents the number of elements. If we have one element, then the maximum sum possible is 7 only. Okay, now what we gonna do is iteratively we iterate over all the elements of the array. Okay, and we fill this DP. That means we have, let's say name it as memoization, because we are doing memoization. And when we are filling this memory location, what we have two choices: either take this element and add it with this element, because we can't take this element. If we take this element, then it will be adjacent to this element. So we have two choices: either take 10 or the element 1 before 7, okay, that is 0, or simply take the value presented this map, that is 7, and choose the maximum out of this. So we have 10 and 7, so maximum out of it is 10. So next, if we want to fill this location, then we have two possibilities: either take 12 or the maximum value up to this location, or simply take this value. So we have maximum, so in this location we have 12 plus 7, or take simply 10. So the maximum is this 19, so fill 19. Next, when we want to fill this memory location, we have two possibilities. We have 7 along with the value present 1 before 19, that is 10, or simply take 19. So maximum of this is 19, so simply put 19. Then what we have this 9 along with the value 19, or take the value 19 only. So we know that 19 plus 9 is 26, so maximum is 26. Then if we want to fill this memory location, then we take 14 along with 19, or take 26 only. So we know that 14 along with 19 produces the maximum sum, that is 33. So with 6 elements, the maximum sum which is produced is 33. So if we analyze the time complexity of this method compared to the one which we just described earlier, the recursive method, so in this we are creating an array of size equal to size plus 1. So creating this array cost O of n. After that we iteratively iterate these all array elements once only, so which will cost in O of n only. So effectively the complexity of these operations order of 1 only. So in the earlier case the complexity is exponential, so it boils down to O of n in this case. Okay, so now let's check the code of this method, and I will show you how to use the dynamic programming. So let's say if we created a method 2 which is a dp. Okay, so we are passing the array, along with that we are passing the size of the array. Now if size of the array is 0, then we have to simply return 0, and if size of the element is 1, then we simply return the first element. And what we're gonna do is, now we're gonna iteratively go through each and everything. Okay, so what we have, this elements 7, 10, 12, 7, 9 and 14. So these are the elements. Okay, so currently we handled both the base cases. Then we will create one map of size 1 greater than that, and we fill this size and fill the first element to the 0, because with 0 elements we have a maximum sum of 0. Now we fill the first value to be array of 0, because with 1 element we have the maximum sum as the sum of the first element, that is that element itself. Now iteratively we iterate through the second element, and store the values or the maximum sum up to that location into this map or memo. So what we have memo of I is equal to max of, we have two choices. Okay, so simply take memo of I minus 1, or array of I minus 1 plus memo of I minus 2. Okay, so what this effectively is, we have this array and we have created a map. Okay, so first element is 0, second element is 7 in this memo. Okay, now whenever we are filling the third location, that means the second index, we have two choices. Either we can take this 10 and sum up with this 0, that is this only, that means we are taking 10 and sum up with 0, or simply take the value just before it, that is this in the memo, which is the maximum up to this memory location. So we have maximum as 10. So like on, we fill all the memory locations of this memo. Okay, so this is a simple iterative method, and by doing this we are filling the memory location memo. Okay, after that what we gonna return is whatever is the present in the last this location we are returning as our answer. Okay, so for calling this, what we gonna do is we gonna call the method 2 along with the array element, and here we are not passing the index, here we are passing the actual size of the element. So now let's try this out. We have this, see, in this case also we are getting the answer is 33. Okay, so what we did in this method is, let me iterate over this again. So we are creating a map called memo, and we are filling the first and the second location, that means maximum sum with 0 elements and maximum sum with 1 element, and for maximum sum with 2 elements and so on, we are iteratively going through all the elements of this array and fill this memo. So this is only the one time operation, because we are going from starting index to end index only once. So this will cost around order of 1 only for each array location. So effectively, if we write down the time and space complexity, the time complexity for this is O of n only, because we are iteratively going from starting to end location only once, and the time space complexity is also O of n, because we are creating an extra array of size s. Okay, and here n is equal to s. Now these are the two methods which we come up with. Now think of, is there any other method by which we can solve this question? So let's see that out. See, we have 7, 10, 12, 7, 9, 14. These are our array elements. Now I will show you the next method, in which we just want to iteratively go over all this element once only. That means it will take off and time, and without taking any extra space which we take in the case of the DP in the earlier part. So this code will be done in O of 1 space complexity and O of n time complexity. So let's look that out. We are creating two variables, first and second, which will keep track of the sum up to this location or the one just after that. Okay, let's see that. First is initialized with the value 7, the first element, and the second is initialized to the maximum of the first and the second element, that is 10. Okay, so this is the base cases which we need to handle. After that, what we gonna do is we have to iterate from this 12 down to 14. Okay, so whenever we are at this 12, we need to find out whatever is the maximum of 12 plus first and second. Why we did that? Because first will contain the value excluding this adjacent element and second will contain the value, maximum value up to this part with this without this adjacent value. So maximum of this 12 plus first, that is 12 plus 7, and maximum of second is 10. So from these two values the maximum come out to be 19. So let's say if we take one more variable current which will hold the maximum of that particular point. Okay, so we have 19 in our current variable, so we replace this first with the second value, because when we jump to this memory location the first will be maximum up to this part. Okay, so first will be changed to 10 and second will be changed to the current maximum. At any point of time, second variable will contain the maximum value up to that points. So okay, so it will contain 19. After that, when we jump down to 7, so the maximum value up to this point is either 7 plus first, that is 17, or the second, that means if we do not include this value, so that is 19. So maximum of these two is 19. So first will contain second value, that is 19, and second will contain this current max, that is 19. After that, when we jump to this memory location, that is 9, the maximum value up to this is 19 plus 9 or simply 19, so that is 28. So the second value will contain 28 and the first will contain the value of the second, that is 19. Then we jump down to 14, so maximum will be 14 plus first, so first will contain 19, or either it could be second will be 28, so maximum of these two will be 33. So first will contain 28 and second will contain the maximum current up to this point, that is 33. So at the end, second will contain the value of 33, that is the maximum sum with no adjacent elements. Okay, so now let's look at the code of this. For this we will create one method. In that we are passing our array elements along with the size of that. Okay, so we have to first handle the base cases, that is if size equal to 0 we are simply returning 0, because with 0 elements there is no maximum sum possible. If size is equal to 1, simply return the first element which is present as index 0. Now as we discussed, we will be going to take the two variables, that is first and second, and the first will be initialized to the first element of the array and the second will be initialized to the max of the first element and the second element. Okay, so as we discussed in this, we have 7, 10, 12, 9 and 14. 10, 9, 7, 10. Let's check the example again, that is 7, 10, 12, 7, 9 and 14, and our first variable and the second variable. The first variable is initialized to the first value and the second variable is initialized to the max of these two values, that is 10. After that, what we have, we iteratively go from the second memory location down to size s, and at each point we are finding the current max. that is max of the current index value with the first, and if we are not taking that element, then simply second, and change our first variable to second and second to the current max which is there. Okay, so effectively what we are doing is when we are at this memory location, we take the maximum of 12 plus first and the second. 12 plus first indicate that if we include this element, then we are no chance of taking this element, that is the maximum up to present at this, which will contain in first. So it will be 19, or simply take the second one, that means do not consider this value. So maximum of this is 19. So change the first to the second, because when we jump to this location, the first will be the maximum up to this, and second to the current max. Okay, now second will contain the maximum value or the answer, so we simply return this second. Now let's run this. Okay, so we have to call this function from mean also. Method 3, which we are passing array elements and size of the array. Now let's look at this. See, 33. So this are the third method. This is the third method. Let's analyze the time and space complexity. For time complexity, it will be O of n only, because we have to iterate through each and every element of the array. But when it comes to space complexity, it's boiled down to complex, or let's say constant space complexity from this linear complexity. Because in the method 2, what we gonna do is we take the extra array of size equal to that array, but in this case we are maintaining just two variables, first and second, which keep on holding the values and changes accordingly, and effectively gives the answer in the second variable. So effectively I will taking no space in this, so we are doing this in O of 1 space complexity. So these are the three methods which we discussed in this section. Now whenever you encounter this question in any interview, so simply do one thing. Instead of jumping direct to this method of dp or the constant method, first explain this method, that is recursive method, which will take exponential time and logarithmic space complexity of the stack. After that, jump to this method, that is method 2, which is the dp version of this. So explain this part, which will effectively take O of n space and O of n time complexity. And when your interviewer asks you to do more optimization in this, then jump to this third part, that will give you the space complexity of constant. So these are the three methods of solving this question. Hope you like it. So in the next section I will be explaining some more questions on dynamic programming. So till then, stay tuned. Bye.